we finished last time talking about Hopital and how we could use it basically in limits, and therefore use it in our deciding if our sequences converge or diverge here. So here are some commonly occurring limits that you probably want to have down pretty well. Natural log of n over n as n goes to infinity is going to be 0. Okay, so as we go to infinity, that n on the bottom is going to blow up way faster than the natural log on the top. If you think about how they're graphed, natural log does like that, and whereas n does like that. So it's going to get, the numerator gets a lot bigger than the denominator. The nth root of n, this one, any guesses? Ooh, close. 1. 1 goes to 1. We can almost play the does it go to 0 or does it go to 1 game. Root 3 to the 1/3, 4 to the 1/4, 5 to the 1/5. But they're getting closer and closer to it. Yeah. So then we've got the limit of as n goes to infinity of x to the 1 over n. Anybody? 1 or 0?
0.
Okay. One of you has to be right. It's 1. So, that's when x is greater than 0. What about limit as n goes to infinity of x to the n?
That seems like it's sort of. Oh wait, no. That probably needs to be 1.
Now, if we're just going to n goes to infinity, that's one thing. But what if we're restricting x to be less than 1? Like 3/8. So we're not changing x here. So what happens if we restrict x to being essentially between -1 and 1? What do we think there then?
One or 2. I just want to use.
What's going to happen there?
That's going to keep it small.
Right? Because that denominator is going to get bigger a lot faster, isn't it? Like if this was 3/8 squared, right? So, and if we're between 1 and 1, that denominator is always bigger. So this one is 0. All right. What about this one for any fixed x? Not just one that's between -1 and 1. What about for any fixed x? I will be very impressed if anybody recognizes this one.
It would be 1 plus, it would be 0. I don't believe it would be 0.
Nope. Not 0, not 1. It's the only one on this page that isn't 0 or 1. Patrick, you recognize this one?
Would this go to infinity?
Nope. It's going to go to a number that's not infinity. Yeah. That's our exponential right there. 1 plus 1 over n to the n is, and you take n to infinity, it's for compounding interest. And as you compound that interest out to infinity, or compound it instantaneously, then it gets to that that the exponential Euler's number. Okay, and then this last one, fixed x again. I mean, what gets bigger faster? Something to the n power or the n factorial, right? As we go to the, as we'll go to n. So this will be 0. Okay. Any questions on that? No? Okay. Let's take a look at recursive definitions for sequences here. So here, what we're going to get is the first term or two, and then you have to use the recursion formula to figure out remaining terms. So write out the first 5 terms. So we'll do this first one together. So we have A1, that's 1. And then they tell us that any other A to the n, or any other value, is just the previous value plus 1. So for A2, it's going to equal A1 plus 1, which is 1 plus 1, which is 2. Right? For A3, it's going to be A2 plus 1, which is just 2 plus 1, which is 3. And then A4 is A3 plus 1, which is 3 plus 1, which is 4. And A5 is A4 plus 1, which is 4 plus 1, which is 5. Okay. Any questions on that? Let's try this one then. You tell me what to do. What is it? What am I going to get? A2. So A1 is 1. It'd be 2 times A1, which is 2 times 1, which is 2. Okay. What about A3? 3 times A2, which is 3 times 2, which is 6. A4. And then the last one, A5. Which would be good. Okay. And you can keep going from there, but they just wanted the first 5. Anyway. What is this? Well, think about this. This first one starts off, we have 2 times 1. Then the next one, we have 3 times that result. That's 3 times 2 times 1. And then the next one, we have 4 times the previous result, which was 4 times 3 times 2 times 1. Yeah. Just recursively. Okay. Now go ahead and try this next one. Pause this for a few minutes. All right, so for this one, our pattern is the next one is the previous 2 added together. Anybody know what that is? Well, the first, I mean, what sequence is that? Okay. So we have A1, A2, so we need to start with A3, right? So A3 is going to be A2 plus A1, which is going to be 1 plus 1, which is 2. A4 is going to be A3 plus A2, which is going to be 2 plus 1, which is 3. A5 is going to be A4 plus A3, right? So that's 3 plus 2. So this is 5. And then 8. And then 13. And then 21. And then 34. And then 55. And then 89. So on and so forth. Right? What is this? It has a special name. It has a lot to do with what we humans like the look of, surprisingly. And I'm not sure why. Huh? Fibonacci sequence, yep. This is the Fibonacci. Very interesting is the golden ratio falls out of the Fibonacci sequence naturally. There's a couple of ways you can get it. If you go to large enough numbers, then the ratio of two consecutive numbers starts to approach the golden ratio. So you can approach the golden ratio by going really far into the sequence. Or you can, how many of y'all ever had linear algebra? You ever do eigenvalues? Okay. Well, I'm sure at some point you'll have to take linear algebra. So what you can do is there's something called a propagator. It's a little matrix that's 0, 1, 1, 1, I believe. And you apply it to any two consecutive members of the Fibonacci sequence, and it gives you the next two. 0 times 1 plus 1 times 1 is 1. 1 times 1, right? I'm doing 1 times 1 plus 1 times 1, that's 2. Like that. So you propagate through by doing this matrix multiplication. It gives you the 1, 2. If you then take and do, 0, 1, 1, 1 times, we can do 5 and 8. Let's say another consecutive pair. We'll get 8, 13. 0 times 5 is 0. 1 times that is 8. And then 1 times 5 is 5. Plus 1 times 8 is 13. And so it will actually walk you through the Fibonacci sequence. Well, when you later learn what eigenvalues are and eigenvectors for linear algebra for matrices, they are actually, whenever you multiply things by matrices onto vectors, they cause them to rotate and stretch. Well, there are certain vectors that when you multiply a matrix onto specific vectors, all it does is stretch them. It doesn't rotate them. And so it makes it really nice because it only makes them longer. So you don't have to worry about the rotations. It's very helpful in physics, very helpful in quantum mechanics, actually. You're always trying to look for a basis where your situation is all just multiplying with eigenvectors, so that's all you're doing is stretching and not worrying about rotations and stretches. It makes the math a lot easier. You can decouple things with it. There are also things called eigenvalues, and these are the amount by which those vectors get stretched, right? These values that fall out of it, they're called eigenvalues. And the eigenvalue, one of the two eigenvalues for this is the golden ratio. The other one I think is called the silver ratio, maybe. It's very similar. But yeah, it's the golden ratio, which is the ratio that artists for a long time have used because humans find it the most appealing. They'll make things this ratioed out. And I mean, I have known this. So moving on from there we go, something that looks very designed in mathematics, Fibonacci sequence. We can go over to here and let's look at a bounded sequence. So a sequence A sub n is bounded from above if there exists a number m such that, in fact, there can exist multiple number m's, but as long as we have at least one number m such that any a sub n is less than or equal to that value of m for all n. In other words, you know, we never get above that value. So then we know that it is bounded above. The number m is the upper bound for a sub n. I almost want it to be an upper bound, not the upper bound. An upper bound for a sub n. If m is an upper bound, see how we can have more than one, for a sub n, but no number less than m is an upper bound as well for a sub n, then m is the least upper bound. The least upper bound. So if we have a sequence that approaches 1/2 and never gets above 1/2 and gets closer and closer to 1/2, well, 1 is an upper bound, 10 is an upper bound. They're all bigger than that, right? But 1/2 would be the least upper bound. If we go anything below 1/2, then we're into the sequence. Make sense? Okay. So we can have a least upper bound. So let's consider this example. N over n plus 1. So as you look at this one, you start off with 1/2, 2/3, 3/4, right? 4/5, sorry. 4/5, and we just keep going like that. And so when we do this, we're going to get closer and closer to what value? 1. But we're never actually going to get to 1, are we? So what is our least upper bound for this? 1. So m equals 1 is least upper bound, right? So in other words, we're never, come on, give me a color. We're not getting across this 1 right here. There we go. I know that was an impressively straight drawn line, right? Okay. All right, m equals 1 is the least upper bound. So similarly, a sequence a sub n is bounded from below if there exists a number such that, and we'll do little m here, is always less than a sub n. Okay, so same sort of thing, we just never get below that point for all n. The number m is the lower bound for a sub n. I should say, I think it should read an. The number m is a lower bound, not the. I guess it, no, I don't think. So if m is a lower bound for a sub n, but no number greater than m is an upper bound for m, then m is the greatest lower bound. Then I think those should all be lowercase m's, not those capitals. Okay, if we were using the lowercase one for that. Our greatest lower bound. Get it right eventually. If a sub n is bounded from above or below, then a sub n is bounded. If a sub n is not bounded, then we say that a sub n is an unbounded sequence. Okay? If it's not bounded, it's unbounded. If it is bounded, we say it's bounded. Okay, y'all want me to repeat that a little slower? I do like it when they name things that make sense. You know, sometimes they name things and you're like, wow, that's not a good name for it. Like if you're in physics and the electromotive force, it's not a force. Nope, electromotive force is a voltage. It's a potential. It's not a force. So kind of confusing. Or, yeah, those are pretty good. And then planetary nebula. They have nothing to do with planets, but they're called that. So a planetary nebula. That's from astronomy.
I mean, I know this one was showing, it's just that like, it doesn't make sense that they call it a planetary.
I think they thought it had to do with planets at first, but they've more recently decided it has nothing to do with planets. It's the opposite of what they thought it was. So anyway, a sequence, so we're going to monotonic sequences. Basically monotonic function, anybody know what that is without reading up there? Is a function that is always either non-increasing or non-decreasing. You don't want to say it's a function that is always increasing or always decreasing because it might go constant. So non-increasing means it's always decreasing or constant. And non-decreasing means it's always increasing or constant. So we say non-increasing or non-decreasing. Well, we can have a sequence that is always either non-increasing or non-increasing. So if that is the case, we say the sequence is monotonic. All right, if it's always either non-decreasing or non-increasing. And so this we get theorem 6, the monotonic sequence theorem. If a sequence A sub n is both bounded and monotonic, then the sequence converges. And that should hopefully make sense to you. We need both of those things to then say that it is convergent, because it could have an upper bound, but decrease, right? And then it's not converging, right? If it's, like say it was doing something like that, and then it did this, it went back down. Well, then it didn't converge, right? So we need it to be both bounded and monotonic, never changing direction. If it's going up, stays going up or goes to constant, but doesn't start going back down. Yes, well, yeah, but those are functions. And we're talking about, it could be, I guess, n squared from n equals 0 or 1 to infinity. Yeah. Okay. So let's look at an example of this. It says here, show that n over n plus 1 converges. So let's do this pretty easily here. If we look at n over n plus 1, that's going to be 1/2, 2/3, 3/4, so on and so forth, right? We were just working with this one on the previous page. So we can tell you right now what we learned about it in the previous page is it's bounded by 1, m equals 1, right? Didn't we just do that? So this is bounded by m equals 1, and we know that this is never going to decrease, right? So and is monotonically non-decreasing. And then we can just say, therefore, by that MST, our monotonic sequence theorem, I'll write that up here, MST, okay? MST, n over n plus 1 converges. There you go. And I think that is it for 10.1. So go ahead and stop.